Hello there. I wanted to quickly ramble on about 2's complement, which is a way of representing signed numbers inside of the old computer. So first, let's look at these 8-bit patterns, all the possibilities of combining 3 bits total. And 3-bit numbers are not very common inside of computers, but they are quite convenient for fitting on this constrained slide canvas we have. So first, let's just look at the usual mapping between these bit patterns and the natural numbers, an unsigned integer, if you will, starting from 0 up to the number 7. All zeros is 0. 1 is 1, and then, well, we run out of binary numbers, so we have to roll around just like our intuitions for decimal math. When we reach 9, we run around, but that's base 10. In base 2, we only have the numbers 0 and 1, so we have to wrap around and so on and so forth. We continue in that way to the very end. So the other cool thing is if we add 1 and 3 in our heads in this mathematical world, we'll get 4. And similarly, inside of the computer, we can add the bit pattern for 1 and the bit pattern for 3 using the digital analog of the numeric plus operator, which is an adder logic gate, so something etched into silicon. When provided the right voltages, will result in a bit pattern that mirrors the correct result for the mathematical analogs of those bit patterns. So it all sort of holds together. I did another video on homomorphisms that goes into that. But that's great and all. The question is, however, how do we represent signed numbers? So we're limited. We have these 8 patterns, and we basically just have to pick some numbers to map each bit pattern onto. So how can we do that to fit some negative numbers into this bit space that we have? Well, one potentially simple, trivial solution would be, what if we just shift the number line over? We just kind of push off those higher numbers, goodbye 4, 5, 6, 7, and just bring in -4 through -1. So we've kind of split this down the middle between negative numbers and non-negative numbers, and it all sort of is the same contiguous number line. Very neat. And this would be fine. In general, there's nothing necessarily wrong with this, but there are a couple of properties that it lacks that make it not the most desirable choice. If we bring back our unsigned numbers for comparison, we'll first notice that, well, the numbers 0 through 3 do not overlap in these bit patterns. They're represented with different bit patterns. So 2 is 0, 1, 0 in the unsigned mapping, and it's 1, 1, 0 in the signed mapping. Which means a few things. It has some consequences. One of those consequences would be if we wanted to reuse those same logic gates that are very efficient and operate on bits, and they do preserve the addition operations on these unsigned numbers, so 2 plus 4 equals 6. If we want to use that same logic gate with this other interpretation, same bit patterns, right? It doesn't care about the interpretations. It works on these bit patterns, and we were able to figure out a way to map that correctly to unsigned addition here. Or rather, we constructed the gate to map that correctly and to preserve that homomorphism, but whatever. If we try to reuse that with this mapping, this interpretation of signed integers, well, we're going to get -2 plus 0 equals 2, which is bad and wrong. So we would have to invent whole new logic gates, different circuits, probably make CPUs maybe even prohibitively complicated, because we would have to use different components for adding unsigned and signed numbers. They just are completely incompatible. And that would certainly make all of our computers a few orders of magnitude slower, or maybe just impossible to construct altogether. So let's solve the first problem. We want to make sure that 0 through 3 share bit patterns. So let's just shift 0 over 4 positions. And maybe we'll wrap the negative numbers around, because we still want those negative numbers in there. So we'll just have them wrapping around, still going from low to high, because, that's sort of the convention here. If you add numbers, they get higher. So maybe we'll keep that around. So we have 0 to 3, and then we wrap around and go -4 to -1. So it's kind of just like if we go from 0 to 7, and then, well, we run out of room, so we have to wrap around in a sense. Here, we've just kind of cut it in between. The Mobius strip was cut in the wrong spot, perhaps. It's a little weird, but let's just explore this. Firstly, it does have the benefit of 0 through 3 have the same bit representations. So 2 and 2 are 0, 1, 0, 3 and 3 are 0, 1, 1. Like, these overlap. Perfect. So that we have that shared space. We don't have to worry about encoding them differently. And then let's look at what happens if we perform some operations. So if we take 2 and add it to 4, or rather add these 2 bit patterns together that we interpret as 2 and 4, well, the result of that logic gate addition will result in the following bit pattern, which is the bit pattern representing 6. And now, running those same logic gates, if we just look at our different mapping here, 2 is still 2, but 4 is now -4. And 2 plus -4 does actually equal -2, which is our mapping for that same bit pattern that was mapped to 6. So both of these formulas hold. This is correct. That is the right interpretation. We haven't gotten some busted math. And that is actually, this is the representation known as 2's complement. And it's how signed numbers are represented, precisely because we can reuse the logic gates and we can reuse that bit space for the positive numbers. So everything can work very efficiently. And we basically can just choose to interpret numbers differently based on the types in our programming language. But all the addition will hold. Further, we didn't look at this yet, but what if we add 2 to 7? So we'll start at 7, adding 0. And then when we add 1, what actually is going to happen is that it's going to wrap around, and we're going to end up with 1 as our result. And this is just a consequence of the fact that we have a limited amount of states that we have to map to these numbers. Numbers go on forever, infinity in both directions, but we can only represent so many possible states with 3 bits, 8 of them to be precise. So logic gates happen to wrap around. Let's look at that same operation when interpreting 2 signed numbers. So in this case, it'll be 2 plus -1. And those logic gates, when you add them, will output 0, 0, 1, which in this case is the number 1. But 2 plus -1, or rather 2 minus 1, is indeed 1. So in this case, that effect of wrapping around actually is correct and does preserve our intuitions for how adding positive and negative numbers work, which is pretty neat. So each representation does have an issue of this boundary where it eventually runs off the top. And this is why if you've ever added some very large ints together, you'll eventually get a negative number, even though all you've done is add numbers together. And that's because you've sort of shot past the positive number space and landed in the negative dead zone. But the same thing could happen with positive ints, in that they'd wrap around and end up as a very low number. And that's really it. I mean, that's it's kind of obvious. It's not that crazy. It's a bit intuitive, I would say. Usually these things are explained in a very roundabout manner, saying like the first bit represents the sign, which technically is true. 1 is in this first position, this most significant bit in the signed representation. But it's not so much. It's not equivalent to just putting a minus before a normal number, because this representation 0, 0, well, that's 0, and 0, 1 is 1, but this is -4 and -3. So it's not just the existence of that most significant bit being a minus sign. And I feel like that's kind of the first intuition one might have, is someone tells you, oh, that is like representing the minus sign. It's not really it at all. I don't even like thinking about that. Okay, so one last bonus, piece of information here is, what if you want to negate numbers? What if you want to go from 1 to -1 or 2 to -2? How can we do that? Can we figure out some operation, some pattern that will make this work? And we can notice, if we do this, that, well, the numbers seem to encroach upon one another, get a little closer, but looking at the bits might not be obvious exactly if there's any pattern here at all. So let's instead move ourselves in from the very ends. So 0 and -1, and then so on and so forth. Can you notice any pattern in these bits? And I think you probably can if you pay close attention. Maybe this one will be the most obvious. They're all flipped. So 0, 0, 0 becomes 1, 1, 1, 0, 0, 1 becomes 1, 1, 0, 0, 1, 0, 1, 0, 1, etc. And then if we take that knowledge and look at this negation case that we're looking for, well, 1 to -1 and 2 to -2, it encroaches in that by 1 position each time. And it looks like, actually, if we go from 1 to -2, which is sort of its opposite position, where we flipped all the bits, our target is just 1 over to the right in all of these cases. So you flip the bits, you flip the bits, you flip the bits, you land 1 short. So the way you negate a signed number is by first flipping the bits and then adding 1. And that'll always work, which is kind of fancy. Okay, that's it from me. Ciao.